everyone. Thank you for virtually attending our talk. Today, Neil and I will present the results of our research on automated firmware analysis, research that we conducted together with these amazing people that you see listed in this slide. Why should we analyze firmware? Well, I'm sure that if you attend this talk, I don't need to explain and convince you that IoT devices are nowadays extremely popular. And there exists a very large amount of different devices, smart toasters, smart lights, smart switches, and now we also have a smart X-ray. It's not clear to me what this is supposed to do. But anyways, the common thing is that we have seen that the firmware running on these devices is often vulnerable. And not only these devices contain dangerous vulnerabilities, but we have seen these vulnerabilities being exploited by attackers in the wild. And here, the most famous example is probably the Mirai botnet, where thousands of IoT devices were compromised to perform a large distributed denial of service attack. Now, one interesting thing is that many of these vulnerabilities that we see in these devices are actually quite old types of vulnerabilities, things that we have known for a long time and for which attackers do not really need any sophisticated exploitation technique. And in fact, firmware often does not present many of the protection mechanisms that we are nowadays used to in comparison with modern operating systems. So I'm thinking at, for instance, randomization or control for integrity. But at the same time, firmware presents some significant differences when compared to, for instance, desktop applications that make security analysis particularly difficult to apply. So first, firmware is very hardware dependent and it relies on a lot of peripherals. Just think about a smart camera where the firmware is programmed to directly talk to the camera sensor to retrieve images from the outside world. But also firmware lives in a unique and minimal environment with no standard configurations. And indeed, for performance reasons, firmware does not present many of the advanced features that we are nowadays used to in modern operating system. And finally, embedded device rely on different architectures, sometimes proprietary, and this makes things a little bit more tricky. So if we want to analyze a firmware image, what we can do, we can try first with dynamic analysis, right? So we imagine we can emulate a firmware image and we can run our coverage guided FADS. Well, unfortunately, dynamic firmware analysis is particularly difficult and currently not very reliable. And there have been recently some very promising works in this direction, but we're not there yet. And the main reasons, again, are that firmware is heavily hardware dependent. So this means that a proper dynamic analysis environment has to model peripherals, has to model interrupts, DMA, but also deal with shared memory, hard-coded addresses, and sometimes unmodeled architectures. So all these things are quite complex to design and implement. So as an alternative, we can try static analysis that instead does not suffer from many of these limitations. And the problem here is that current approaches do not scale. And in fact, they produce many false positives. The main reason for this is that firmware is mostly multi-binary. In fact, the vast majority of firmware is Linux-based, and in practice, it consists in a squash file system that contains hundreds of executable programs. So you can see in this example a firmware image that contains 240 executable binaries. But on a larger scale, we have seen in our dataset that contains more than 900 samples that a firmware image on average contains more than 150 binaries. Of course, not all of these binaries are actually needed and used to implement the firmware's functionality, but some of them do. And the typical architecture of an embedded system contains a binary that we call the border binary that receives requests from the external world. This is typically a web server, and that this binary forwards the request to an handler binary that instead processes the request and returns a result. In practice, this is a little bit more complex because we can have many of these handler binaries, and each of them can further interact and share data with additional programs. So now the question becomes, which binary should we look at for a security analysis? Because clearly On the one hand, if we only look at a subset of these binaries, or for instance, if we only look at the web server, then we will miss potentially many vulnerabilities. So we might have potentially many false negatives. But on the other hand, if we apply current approaches to analyze each of these binaries individually, then we will have a large amount of false positives. And we can see an example of this here in this example that is a simplified version of a real-world firmware image. And you can see here on the right a program that reads data from two environment variables. And if we assume that these two variables represent the input of this program and this input is controlled by an attacker, we clearly see that this program contains two vulnerabilities. So here there are two buffer overflows where this data read from the environment variables is used in unsafe string copy without checking the size of the destination buffer. So easy two buffer overflows. But in this specific example, in this specific firmware image, this binary on the right is only executed through this binary, this program on the left. And we can see here that this program indeed sets the value for these two environment variables and then executes the program on the right. And now, if we actually look at the big picture and we consider the interaction between these two binary, we can see that there is actually only one bug, only one vulnerability. And in fact, while the value of the query string variable is potentially unconstrained and can be longer than 128 bytes, so producing a buffer overflow, the value of the log path variable is hard-coded and is constrained to a string that is shorter than 128 bytes, so shorter than the buffer size, and so not producing any buffer overflow. This is just a quick example that shows how false positives may arise when we look at binary individually. And of course, you can imagine that when we scale this up to many binaries and many firmware images, the number of false positives will drastically increase. So in our research, we started from the observation that firmware is mostly composed by multiple interacting components, multiple interacting binaries. And we investigated this observation and found out that modeling the interactions between these binaries is essential for an effective analysis. And we can do this because programs and processes communicate through a finite set of methods, a finite set of inter-process communication channels that we can model to introduce static multi-binary taint analysis. So multi-binary taint analysis where data flows and constraints are not only propagated within one binary, but also from one binary to another. We built a prototype on top of this approach, Caronte, and we will show in this presentation that Caronte is able to identify unknown security vulnerabilities, but at the same time drastically reducing the amount of false alerts. So if we want to look at what Caronte does in a nutshell, Caronte takes as input a firmware image, it unpacks the image and extracts all the different binaries contained in the image. Then it identifies what we call the border binaries, so those programs that receive user input from the external world. And once we have these border binaries, Caronte starts identifying and tracking the interactions with additional binaries. So we can see in this example that these two binaries interact through an environment variable. So in practice, what happens is that these two binaries know the value of the name of this environment variable, and we call this the data key of the communication, and using this data key, they are able to share data. And of course, each of these binary can then itself further communicate and interact with additional binaries, as shown in this example. So now we have modeled all of these interactions. We have this interaction graph that we call the binary dependency graph. Using this graph, we can actually run our multi-binary taint analysis. So we start from the border binaries and we taint user input and propagate constraints from one binary to another. In this example, we see that all these binaries share data that is up to 512 bytes, but here in the very last binary of this path, this data is copied into a buffer that is only 500 bytes. So in this case, leading to a buffer overflow. So I know that given like this is not probably super clear, Now it's time to dive into the details, and I leave this virtual stage to Nilo, which is the main author of this research, and will tell you more about each step that Caronte performs.
Thanks, Andrea. Hi, I'm Milo, and now I'm going to talk about Caronte's architecture. As you can see in these slides, these are the steps of our approach that Andrea briefly mentioned before, and then now I'm going to explain more in details in the next slides. As input, our system takes a firmware, which it unpacks it and into multiple components using the firmware unpacking tool called Beanwalk. Once we extracted all the binaries, we proceed to find those that we call the border binaries. Border binaries are those binaries that interface the functionality of a firmware to the outside world. Our intuition is that these binaries must contain two types of capabilities. They must receive data from the network, and they must contain capabilities to parse this data. To find these binaries, we look for these two capabilities, and we scan each function for each binary in the firmware and collect 5 different features: the number of basic blocks, the number of memory comparisons, the number of branches, the number of network-related keywords. We look for keywords such as SOAP, HTML, HTTP, and so forth. And then we check if there exists a data flow between a read from socket and a memory comparison. Once we collected all these features, for each function, we compute what we called the parsing score. The parsing score basically is a weighted sum of these 5 features. Once we get this parsing score for each functions, we compute the parsing score of a binary as the maximum parsing scores of its functions. Then we cluster these binaries using their parsing scores, using the dbScan algorithm, and we consider as border binaries the cluster of binaries containing the highest parsing scores. Once we get all these border binaries, we compute the binary dependency graph, or BDG. The BDG basically is a graph that models the data dependency across the different binaries in the firmware. To build this graph, we use our static taint engine to taint data that is compared against network-related keywords in the border binaries, and then we run a taint analysis to detect if some data has been shared. In particular, for this second step, we use a set of modules that we call the CPFs, or Communication Paradigm Finders, which basically each one of these CPF analyze each basic block in the taint analysis and understands if the logic of the basic block suggests that some data has been shared within other binaries. We provide Caronte with a CPF for each IPC paradigm, which means that we have a CPF for socket-based communication, a CPF for file-based communication, and so forth. And if a CPF understands that some data has been shared, first, it retrieves the data key. The data key, as Andrea before briefly mentioned, is the endpoint where the data will be available. Example of data keys might be file names or names of environment variables, and so forth. Then a CPF determines what's the flow direction of the communication. It understands whether the binary is setting data for another binary to be retrieved, in which case we will call the binary setter, or if the binary is getting some data from another binary, in which case we will call the binary the getter. Finally, the CPF performs binary sect magnification, which means that the CPF will use the data key to scan the firmware and find other binaries that can possibly rely on the same data key to use some shared data. In case some information are not available, such as symbols are not present, we provide Caronte with a generic CPF that we call the semantic CPF. The intuition behind this CPF is that some data keys must be used as index to set or get some data. As you can see in this simple example, the data key HTTP request is used to index some global structure to set some data. Okay, let's see an example of how we build the BDG. As you can see, in the function parseURI, we have a string comparisons of some data against some network-related keyword. In this case, we would taint the variable p, and as you can see, regardless of the path that has been followed, tainted data is returned by the function. In this case, we find the caller of this function, which is serve request, and we continue our taint analysis. As you can see here, the variable data will contain tainted data, which eventually will be passed to the function setenv. In this case, the semantic CPF will trigger and will understand that some data is shared using the environment. We'll understand that this binary is a setter as it's setting some data to be consumed. And you will understand that the data key in this case is the string query string. Therefore, we'll use the environment CPF, we'll use this data key, look into the firmware, and find other binaries that rely on the same data key. And we will find that this other binary indeed use the same data key. Once we obtain our BDG, we analyze each binary in the BDG, and we collect all the constraints that binaries apply on shared data. And we propagate this constraint to the successors in the BDG. Now, a problem in this case is that in theory we should consider every path in every binary that apply constraints on shared data. As this is in the general case impossible, what we did is that we get the program points where the data has been set and the data has been shared within the same binary, and we analyze every path between these two program points up to a certain time limit, and eventually we propagate only the least strict set of constraints. One might ask, why only the least strict set of constraints? Well, the reason is that our intuition is that under constrained data is more likely to lead to security vulnerabilities. Going back to our example, we know that the variable data is tainted, and we know that it comes from the function parse_URI. As you can see, again, in this function, there are two possible paths that lead tainted data out of the function, but only one of them does not apply constraints on the data. As such, we consider this path, and we propagate the empty set of constraints to the getter binary. The last module of our system is the insecure interaction detection module, where we use our taint engine to uncover insecure attacker-controlled data flows. In Caronte, we look for two types of vulnerabilities. We look for memory corruptions, such as buffer overflows, and we look for denial of service vulnerabilities, which means that we find loops whose guards are totally controlled by attackers. In particular, to find vulnerabilities, we taint data that is set or received by another binary, we run a taint analysis, and we raise an alert if tainted and under constrained data reaches the sink. In our work, we consider sinks memcopy-like functions, which means that we consider those functions that are semantically equivalent to memcopy functions. We consider a sink a dereference of a tainted variable, and finally we consider a sink a comparison of tainted variable in loop conditions. Going back to our example, we know that the variable query is now tainted and unconstrained, and we run our taint analysis, which eventually will lead us in the function process request. As you can see here, tainted data, the variable query is compared against some constant string, and the result is set in the variable q, which will be tainted as well. Eventually, the variable q will be used in a string copy operation, and Caronte will understand that first the variable q is tainted and unconstrained, and that the variable arg is as big as 128 bytes. For this reason, we raise an alert. Now, another interesting fact in this example is that, as you can see, the variable log path is not tainted, and therefore the second string copy will not raise a false alert. Okay, let's talk about our taint engine. Our taint engine is an improved version of Anger's taint engine. Anger is our binary analysis framework. And we added two features. First, we prioritize paths that we find more interesting. And second, we added what we called taint dependencies. Let's see these two features. We consider a path more interesting than another path if the first one carries on taint information and the second doesn't. Let's see an example of this. Let's assume here that the variable input contain data from the user, and let's assume that it's tainted. As you can see, the variable input is passed to the function parse, which contains a loop. Now, in this case, this loop might have, in theory, an infinite number of paths, but if you see, only a subset of them lead the taint out of the function. In this case, we consider these paths more interesting than the other paths, and we prioritize them. How do we do this? For each function, we find the basic blocks that return non-constant data, and we follow these returns before considering other paths. Our second feature is what we call taint dependencies. Taint dependencies aims at alleviate overtainting issues. Proceeding with our example, we know now that the variable cmd is tainted, and as you can see, the variable cmd is passed to the function string len. Now, let's assume that the function string len is not analyzed, for instance, because either the body of this function is not present or because some limitation in the static analysis, such as a limited call stack. What the taint engine will do is that we'll create another taint tag for the variable n. So this means that the variable n and cmd will both be tainted, but with two different tags. Now, following the data flow of this program, we see that the variable n is constrained between the values 0 and 511. In this case, the variable n will be untainted, but the variable cmd will not, which in this case might cause the string copy to raise a false positive. Now, what we can do is that we can create a dependency between the taint tag of the variable cmd and the taint tag of the variable n, and if n gets untainted, we can untaint cmd as well. In this case, the string copy will not generate a false positive. We did this in Caronte, and we also automatically find functions that implement string len semantically equivalent code and create taint tag dependencies. Okay, all of this is very cool, but does it work? We ran an in-depth evaluation, and we analyzed 53 devices from 7 different vendors, and we found 46 new zero-day bugs, and we discovered another 5. Now, not only Caronte found new bugs, but it decreased the number of generated alerts from more than 900 on average to 5 per firmware, which means that it's a reduction of 2 orders of magnitude and a low false positive rate. As you can see in our experiments, we analyzed each binary in the firmware independently, and this analysis raised more than 36,000 alerts, and the whole analysis took 18 days. On the other side, we're running Caronte, our system generated only 74 alerts, and the overall analysis completed in 34 hours. We also performed a large-scale evaluation where we consider 899 firmware samples from 21 different vendors. We found that 348 firmware samples contain multi-binary interactions, and Caronte overall generated a few more than 1,000 alerts. In particular, Caronte generated 2 alerts per firmware sample on average, and of all these alerts, we manually inspected 100 of them randomly. We found that 44 to be true positive, and then that 30 of them were actually multi-binary vulnerabilities, which means that we found these vulnerabilities by tracking data flow across different binaries. This slide shows all the results that we obtained in our large scale evaluation. I understand that there's a lot going on this slide, but I'll summarize these results in the next slides. First off, we looked at the size of the BDG, and we found that most BDGs have 5 binaries, but we also found that some BDGs are more complex. As you can see in this example, we found one firmware sample produced a BDG that contained 16 binaries. Finally, we measure Caronte's performance, and as you can see from the first 2 graphs, Caronte scales well in terms of number of analyzed paths and number of analyzed binaries. As you can see from the third graph, Caronte in some cases took more than a day to analyze some firmware. We investigated and we found that there were some problems with anger. This problem got fixed and we are applying the fix to Caronte. Overall, we can see that Caronte scaled well, and this is because our system only focused on what matters, only focus of a very small set of binaries instead of considering all of the binaries in a firmware. And with this, I will leave the virtual stage to Andrea that he will show us a demo of our system.
Thank you, Nilo, for the detailed explanation. Now you know how Caronte works. Let's see how to run it. So we released all our code on GitHub. You can find it at this URL. And in the README of this repository, you'll also find instructions on how to pull a Docker image that comes with Caronte already installed and ready to be fired. So let's have a look. If I run the Docker container, we can see here we have a folder Caronte, and what you have to do to run our tool is simply preparing a configuration file. This is in JSON, and in the config folder there is both a template but also some example from real world samples. We can have a look at one of them. Actually, we can make it nicer. Okay, so here you can see a list of options that can be set. Actually, the very important option is the firmware path, and is the only one that really needs to be set. And in the vast majority of the cases, all the other options can be left empty, and Caronte will deal with that automatically. And of course, in our GitHub page, you'll find a proper description for each of these settings and when they should be used. So to actually run the tool, we can simply pass the path to the configuration file. Let's do this now. Okay, here it is. Now Caronte is running and it's starting its analysis. As Nilo mentioned, this can take a couple of hours, so we'll not wait for this to finish, but we can see what happens next. At the end of the analysis, Caronte produces a log file. We can have a look at an example here. This is still in JSON, and here you'll find all the information, the details about the results of the analysis. So we can see information about the binary dependency graph, how the different binaries interact with additional programs. We can see statistics about the execution time, and more importantly, we can also look at the alerts. So the alert that Caronte produced, this is where potentially vulnerabilities might lie. And again, we can see information about the data flow and so on. But instead of looking at this text-based log file, we recently wrote a very simple user interface. Nothing extremely fancy, but if I now run this, and then we can see the results of the analysis in a browser. So we can see here that for this specific firmware image, contains 128 binaries. Of course, and luckily, not all of them process user input, so we can see a rather simple binary dependency graph showed in this picture. The light nodes are the border binaries, and we can see how these programs communicate with other binaries. So we can see here that these two binaries interact using several data keys, and for each of them we can see what are the CPF involved in Caronte in the detection of these communications. Now what we also can do is that we can look at the alerts. In this specific example, Caronte generated 12 alerts. And if I click on the first one, we can see that the path of the alert gets highlighted in the graph. And this alert is generated by a data flow that starts in the HTTPD binary, which communicates with the file access.cgi binary. Specifically, they communicate through this content type data key. And we can see here the address of the buffer containing tainted data, but also the address of our sink. So this is the final step of our data flow, and this is potentially when the vulnerability might be. So now, if I click on the very last binary of this path in this alert, we integrated this with Engel's decompiler, which will automatically decompile the potentially vulnerable functions where our data flow ends up. The decompiler in Engel is still a work in progress, so you can see that the quality of the decompiled code is not excellent, but it's still good enough for us to spot a real vulnerability. And in fact, in this function reads tainted data from an environment variable, and this data is later on used in an unsafe string copy without checking any sides of the destination buffer. So this was a very simple example of what Caronte can do. I invite you all to check it out on GitHub, and of course we disclose this vulnerability and everything else that we found to the affected vendors. We received some CVEs, and many of them already released patches for their images. So to wrap up this presentation, what we achieved so far. We observed that firmware is mostly composed by multiple interacting binaries, and we introduced static analysis techniques to perform multi-binary taint analysis. On top of this approach, we show that our prototype Caronte can effectively discover unknown security vulnerabilities, but at the same time drastically reducing the number of false alerts. And an interesting point of our research is that we found out that despite program analysis a quite complex task, even when applied to a single binary, scaling program analysis to a multi-binary environment is possible because modeling the interactions between these binaries make things actually quite easier. Okay, then thank you again for attending our talk. Just a reminder, there is an academic paper on this, so if you want to read more details, check it out. And of course, we are available and happy to take questions on the live chat, but also feel free to send us an email. Thank you very much.